We can use the fundamental counting rule, permutations, and combinations to help us figure out different probabilities. So let's just take a look at a bunch of different examples. Find the probability of getting 4 aces when 5 cards are drawn from an ordinary deck of cards. So we have an ordinary deck, there's 52 cards in it, and there's 4 aces, the ace of hearts, diamonds, spades, and clubs. So what we want to do is we want to find the probability that we're going to draw 4 aces out of the 5 cards we draw. So if you think about a deck of cards, okay, let's maybe start out with what our total number, because remember, probability is like the events we want to have happen over our total probability. When we think about probability, we're drawing 5 cards, and there's 52 cards to choose from. It does not matter the order or the grouping, so our total number is going to be a combination of 5 cards taken out of 52 total. Now, when we draw those 4 cards, if I want 4 of them to be aces, out of how many total aces are there? And again, order doesn't matter. It doesn't matter if you have hearts and diamonds or diamonds and hearts. So there's going to be 4 total aces, and we want all 4 of them. So we're going to take a combination of 4 aces out of 4. But there's 5 cards drawn. So we draw 5 cards. If we're thinking 4 of them are aces, how many choices do we have for the 5th card? Well, there's 52 cards, so 48 of them. We have 48 choices for our last card. So again, let's kind of talk about this. We're drawing 5 cards. We want 4 of them to be aces. And I wrote it as the combination of 4 taken 4 out of the 4 total. But really, how many different ways can you get those 4 aces? It's just once. So how many times can you get 4 aces? Just once. And then that's how many choices we have for the first 4 cards, or any 4 cards. And then we have 48 for our final one. Okay, so this is getting aces. This is the different number of cards we have to get their 5th card. Over our combination of 5 cards taken out of 52, which works out to be 2,598,960. Believe it or not, this actually reduces down to 1 over 54,145, which is a very, very, very small probability. 0.0000002. So as a percent, if you move it over 2 times, it'd be like 0.2%. The tricky part is figuring out this. So let's try another example. A box contains 24 transistors, 4 of which are defective. If 4 are sold at random, find the following probabilities. So let's find the probability that exactly 2 are defective. Exactly 2 are defective. Well, we're taking 4 out of 24. And again, a combination, because it really doesn't matter what the order is. So that I'm taking 4 out of 4. I'm sorry, 4 out of 24. Now we want exactly 2 that are defective. We know 4 are defective, and again, it's a combination, order doesn't matter, but we're taking 2 out of that 4 that are defective. Then for our other 2. So these are just saying exactly 2 are defective. Our other 2, there's 20 that aren't defective, and we're taking 2 of those as well. We're multiplying it because of that fundamental counting rule, where you take your events and just multiply them together. So when you figure this out, using your calculator, figuring it out using the formula, that works out to be 1,140 over 10,626, which reduces to 190 over 1,771, which is approximately equal to 0.107. About a 10% chance. Let's look at part B. None is defective. So we want the probability that none defective. So when we look at our totals here, again, we have 24 choices and we're choosing 4 of those. If we want none to be defective, well, 4 are, so there's 20 that are not. We're taking 4 out of those 20. Combinations, order doesn't matter. 4 12,845 over 10,626, which actually reduces to 1,615 over 3,542, which is approximately equal to 0.456. How about all being defective? The probability that all are defective. Well, we're going to do the same thing again. We're taking 4 out of 24. And this time, how many are defective? Well, 4 of them are. And we want all of them to be 4. We're taking 4 defective out of the 4, which is just 1. If you think about it, there's just one way to grab all 4 of those defective ones. Over again 10,626, which is approximately equal to 0.00009. Very, very, very small chance that you're going to grab all 4 defective ones. Now part D uses that word at least again. We want at least one is defective. And remember, when we do that, we actually take the complement. We take 1 minus the probability that none are defective. And I'm just going to abbreviate it here. The good news, we already figured out where none are defective. So we're just going to go 1 minus 0.456, and we get 0.544. So about a 54% chance that we're going to draw one that is defective. Again, using our probability rules, we're just in this case throwing combinations in. Let's take a look at another example. Store has 6 TV graphic magazines and 8 newstime magazines. If 2 customers purchase a magazine, find the probability that one of each magazine is purchased. So we want the probability that we have 1 TV graphic, spell it correctly here, and 1 newstime. So let's start by finding the probability of grabbing a TV graphic. There's 6 total, order doesn't matter which one you grab, and I want 1 out of those 6. What's the probability of grabbing a newstime? Well, there's 8 total, and there's 1 out of that 8. So we multiply those together and do our total. There's 14 different magazines, and we're grabbing 2 of them. Again, combinations, because order doesn't matter. They're not ranking or they're not placing. So when you figure this out, you end up getting 6 times 8 over 91, which is 48 over 91, or about 0.527. Really try to break it up when you're given 2 things and find out, you have your total if you're doing a combination or a permutation, and how many you're pulling out of that total. When you have 2 things, you end up multiplying together. Just 2 more quick examples. A combination lock consists of 26 letters. Now we see combination lock and we think combinations. If you look at the very end here though, it says a combination lock is really a permutation lock. So whenever you're doing combinations, they're permutations. It consists of 26 letters of the alphabet, and you're taking a 3-letter combination. So for our first choice, we have 26 letters. For our second choice now, well, you'd think 25, except right here, the same letter can be used more than once. So actually, we have 26 choices for the second and 26 choices for the third. When you multiply all those together, it ends up being 17,576. That's not our answer though, because we want the probability that will consist of the letters A, B, and C in that order. Well, how many different ways can we have an A, then a B, then a C? Just 1. So it ends up being 1 over 17,576. And we can just imagine how small of a chance it is, or how small the decimal number is. One more example. There are 8 married couples in a tennis club. If 1 man and 1 woman are selected at random, find the probability that they're married to each other. So we're going to grab a man and we're going to grab a woman. There's 8 different men and 8 different women for a total of 64. If we want to find the probability that the ones we grab are married, well, how many different married couples are there? 8 out of how many different people? 64, which works out to be 1/8. Using permutations and combinations can help us find the probability of different events. Really focus on, if you're, especially with the combinations, what you're looking for out of how many, and the more you practice it, the easier it'll get.